Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to NPTEL course on groundwater hydrology and management. This is week 6, lecture 3. In this week, we are looking at the important definitions for recharge and discharge, how groundwater enters the aquifer and groundwater storage through recharge, and how to estimate them. In the previous classes, we looked at certain concepts for groundwater recharge. What are the key methods, physical, numerical, tracer methods, etc. Now we will get into some of the actual methods that are used by the Government of Indian agencies, especially the GEC, Groundwater Estimation Committee, and the Central Groundwater Board. These are very important to understand because these equations and methods are used throughout India as a baseline. So it is important to understand these to make sure what these recharges are made under assumptions and how to tabulate them. Let's move on. So the first method is the groundwater recharge estimation method using the groundwater balance method. I won't dwell much on this slide because we have introduced the groundwater balance a lot in this lecture series. The water balance method or groundwater balance method is the same, but in groundwater balance method, it is a more focused on the groundwater. It can be also called as a water budgeting method. So these terms can be interchanged. The first equation, as you saw, was an overall general equation for the basin or watershed, and del S is a change in storage, which is nothing but your precipitation, your Q in, your surface runoff in, and then surface runoff out is subtracted from the total. Your ET is subtracted from the total, and your groundwater in minus groundwater out. So the net is your del S, change in storage. The storage can be multiple storages. One is your tree plant interception storage, one is your surface water storage, one is your soil storage, and then your groundwater storage. So it depends on where you use this equation. Okay, and this equation can be used for overall hydrology and also getting a groundwater recharge. The next one is your specific water balance method for groundwater. It is called total annual recharge. In the left hand side, which is your what you want to find, right? You want to find the groundwater recharge, and the total recharge is equal to the summation of your recharge during monsoon, your non-monsoon rainfall recharge, plus seepage from canals, plus return flow from irrigation, plus inflow from influent rivers, etc., plus recharge from submerged lands, lakes, etc. So your net recharge, let's take a well. And in this well, where are the water going to come? Okay, so as they say, first the recharge through rainfall. Okay, the rainfall can get into the ground and then come as groundwater flow during monsoon. So there is some rainfall during monsoon, and then there is non-monsoon rainfall. Off-season rainfall also sometimes happens. That also recharges. So we're looking at the total annual recharge on the left-hand side. This one. Seepage from canals. As I said, when the dam water is filled up during monsoon, some of the water is channelized to these irrigation fields. The irrigation fields along the way will not have cement line, and those canals would give recharge. Then return flow from irrigation. You take the water from the canals, you take the water from your dam or even groundwater, you apply water to the ground. Okay, so let's say you are applying water to the field. This is your field. You apply water into the field. What happens is the plants take the water, yes, some soil moisture is taken, yes, but you apply more, right? So then the water will eventually go down to the groundwater aquifer. This is called return flow. Very important term in groundwater recharge or also irrigation. They'll ask you, how efficient is your irrigation? Your most efficient irrigation would reduce the return flow. So if you look at sprinklers and or direct irrigation techniques where the drip irrigation is used only to the root zone, only to the particular plant, then the return flow is very, very less. Inflow from influent rivers, etc. When rivers flow, the water can be lost to the groundwater. We saw this losing stream, gaining stream concepts, etc. Recharge from submerged lands, lakes, etc. So all these water bodies that are inside the land can also give recharge. So all this can be estimated using a mass balance approach. In this first mass balance, it is looking at the hydrology of the entire watershed, whereas in the second, it is total annual recharge, which is summation of the individual recharges. Some of these can be calculated using data, some of these could be estimated, but it is good to have data for everything. So multiple equations exist. The drawback, you can make it as big as you want or as small as you want, and then you can keep on adding terms. For example, let's add one more term here. Okay, so you have your total annual recharge and then rainfall is happening, etc., etc. Then I would say that the water is being brought to the houses using pipes. Okay, what if the pipe is leaking? Then there's recharge to groundwater because inside the ground. So you have to think about how, for example, this is the ground and this is your big water pipe connection. There should be some water leakage, and that can also contribute to groundwater recharge. Sewage systems contribute to groundwater recharge. It's bad quality, but quantity, yes, it increases. So countries like Nepal have a lot of these old water supply schemes, and there's always leakages in. Multiple equations exist for water balance, which means you can make it big or small as and specific as needed. But all of this need data. If they don't have data, they'll say it is negligible or they won't put the component on the equation. So a lot of data is needed, and validations of assumptions is very, very important. For example, if you say that there is no return flow in my recharge equation, that means you should make sure that this irrigation compound is not there. For example, in an urban area full of buildings, no agriculture, so then return flow is zero. You won't have any return flow. For example, there's no canals, this goes to zero. So all these assumptions have to be validated by certain logic. If there's no rainfall, then there's no rainfall recharge. So that should go to zero. So all this is very, very important while making these equations for water balance. So the GEC Groundwater Estimation Committee has recommended many methods, and the methods are based on particular sites, particular use of water, for example, urban versus rural water, and also canals and non-canal regions, etc. This book, I've put it there, GEC 1997. Just Google it, you'll find it. It is a PDF from the Groundwater Board, Central Groundwater Board. It's a Government of India approved agency. It's a Government of India's agency. So they give you all these equations and different methods. So when you want to propose something to a village or understand if the village or area is doing good groundwater activities, you could look at this method, estimation method. Let's look at some. For calculating, I'm just taking one example from the book. For calculating the annual recharge during monsoon, the formula indicated below may be adopted. And this is only annual recharge during monsoon. Okay, so it is only the monsoon recharge. If you look at the previous equation, we have total annual recharge is including of monsoon recharge. So let's look at how monsoon recharge is done. So as I said, each component itself will have a water budget. So here monsoon recharge is S plus DW minus RS, where S is given as change in groundwater storage volume during pre and post monsoon period, April, May to November. So that is April, May is your pre-monsoon. This is the typical monsoon period, the JJAS, the June, July, August, September rainfall, and then post-monsoon is November. Okay. So you have the April, May as the pre-monsoon, the summertime. So what is the change between the pre-monsoon and post-monsoon? So pre-monsoon, the groundwater level is low. Post-monsoon, the groundwater level will be high because rainfall, recharge, etc. happen. The subtraction of this is not only the recharge, because there is the component of the soil to allow the recharge to happen. So that is the coming as a specific yield. We'll come to that. Then we have it in units of million cubic meters or MCM obtained as below. The S is obtained as below. It is the area times water level fluctuation. What is the difference in water level times your specific yield? Okay, so you have an area and then the thickness of the water. So that is how the volume comes. Specific yield is a percentage. The areas not suitable for recharge, like high, hilly, and saline area, should be excluded because they're not going to anyway calculate the recharge in these hilly areas, saline areas, because there's no use for the groundwater. Saline areas, if you recharge the water is going to be salty. What is the use of salty water? Nothing. Same way in hilly regions, people don't get wells inside, so you don't even look at the recharge. So the monsoon recharge is given as S plus DW plus certain other factors in negative, which is minus RS, minus RIGW, minus RIS, which is given as recharge from canal seepage during monsoon, RS, canal seepage. IGW is the recharge from recycled water from groundwater irrigation during monsoon. So from groundwater irrigation, please know the terms GW, irrigation, groundwater. So there could be some irrigation using surface water, which is given as RIS. So as I said, you have a field, okay, and this plot can have a canal which brings in water, and because of that there is recharge. Okay, so there is recharge happening from the canal. So this is the canal, and also there is a groundwater which is being pumped and then put on the field, and that water can also get down into the groundwater as recharge. Okay, I'll show it in a well diagram. So for example, you have this as your well. Okay, this is your field. So you have crops growing here. When you pull water and put it down, which is you're pumping water and you're recharging your area, but most importantly, you are supplying water to the plant. You're pulling water and supplying water to the plant. After the plant has taken the enough water, water will still move down and then recharge back. Correct? So this is the RIGW, which is recharge from recycled water. It is recycled from groundwater irrigation during monsoon. So all this is important to understand the different components coming within your equation. So RIGW is a negative because you need to remove that. RIS is a recharge from canal seepage. You need to remove that because all this is double calculating. RIS is recharge from recycled water from surface water irrigation during monsoon. Because what do you want to do in the left? The left, you have only monsoon recharge, which is a recharge coming from rainfall. So it is very important not to double calculate your recharge. So if you're doing recharge estimation here and another recharge of saying seepage here, so you're double calculating the seepage. So very, very carefully do it. If monsoon recharge, you should only look at monsoon recharge, which is your water level, how it fluctuates times your specific yield times your area, but make sure to remove your DW is also added. But after you add DW, you remove RS, RI, GW, RIS. So what is DW? Gross groundwater draft during monsoon, because you have your recharge, which is affecting your fluctuation, but you're also pumping. So when rainfall recharge is happening, you're also pumping. That water is also added to the recharge, because only recharge water you're pumping as knowing. So take the monsoon water, put it into your groundwater as recharge. But while you're putting the groundwater as recharge, you're also extracting water, and that water combines with the recharge to get net recharge. So S plus DW is net, and then you have your removing your double calculations RS, RI, GW, RIS, time your normal monsoon rainfall by your annual monsoon rainfall plus RS plus RIS. Okay, so all this is given as your monsoon recharge. What is RF? It is your rainfall in meters. So this is just a fraction times your thickness plus thickness. Okay, so all this would be your thickness, whereas all these are volumes. And all this is very, very important to understand how you calculate your specific recharges, because in this equation you saw multiple recharges happening, but you should not double calculate, and you have to be very careful in making these water balance equations. I recommend you to go through the book to identify other methods. It is very, very informative, and we can take a whole 2 weeks of lectures based on this book, because it's each and every one method given very specific directions and values. I've taken some in this lecture, for example. Okay. Let's look at it. Rainfall infiltration factor in different hydrological situations. What is the hydrological situation? Hydrogeological, not only geology. When it is geology, it is only rock, sediment, those kind of things. But when you talk about hydrogeological, then water is also part of it. Hydro. Okay. So rainfall infiltration is very important to understand these recharge factors. If you go back to the previous entity, you say that, oh, how much is recharge happening, what is the change in the groundwater storage, etc., etc. But if you don't understand the hydrogeological condition, you cannot do it. And this is where you can estimate based on GEC's recommendations what is the rainfall that can go in, because you may not have data. Again, if all these equations need data, if you don't have the data, then GEC has given you recommendations. Okay, fine. If your area doesn't have data, simply analyze what type of geological situation it is. Let us take alluvial areas. Where are alluvial areas? We have that in the Ganges Basin, for example. Okay, so those areas have sandy soil formations, sandy areas, and areas with higher clay content. So the rainfall infiltration factor, which is how much, here it's given as how much percentage of the rainfall goes into your aquifer through rainfall infiltration, is calculated. And it is given as a percentage 20 to 25, 10 to 20% of normal rainfall. So we have, for example, 100 mm of rainfall, around 20 to 25%. So 25 mm can get into the ground as infiltration. Again, this is not directly going into the aquifer, it goes as infiltration. After infiltration, it can be taken up by the plants, it can be stored in the soil, or go into the groundwater. Moving on, the semi-consolidated sandstones, which are mostly found in the northern regions, okay, along the west and east northern regions, you have some semi-consolidated sandstones, which are less having infiltration capacity compared to alluvial areas, because it is only 10 to 15%. Okay. Then we come to the most predominant aquifer system in India, which is the hard rock area aquifer system. Where the rock is hard, the porous space is fractured, and sometimes the fractures are not connected, so water is not shared. So in that type of area, we have granitic terrain, weathered and fractured, unweathered rocks. So we have 10 to 15% of rainfall infiltrates and goes into these kind of soil formations. Please note that it says 10 to 15 for weathered, which means broken and weathered rock. But when it's unweathered, when it's still fresh rock, we call, or a rock which is not weathered due to conditions, then we just 5 to 10% of rainfall. Okay, so the percentages help to differentiate the type of hard rock aquifer. And then if it is ballistic terrain, it is again 10 to 15. If it is a jointed basalt, weathered basalt is 4 to 10. Jointed means it has more connections into intertwining each other, and that makes the water to flow and store. So you can see from here that the GEC has given you a set of equations. If you can have data, fine. But if you don't worry. Here are the other estimates that you can put into the groundwater equation or groundwater water balance. So you have phyllites, limestone, sandstones, quartzites, shales, etc., which are 3 to 10%, very, very less. And unfortunately, this is the hard rock aquifer system in most of India. Moving on. Recent groundwater data. Okay, so let's look at some recharge estimation methods based on groundwater data. The previous was the hydrogeological condition, the rainfall, etc. Now we're going to look at only the groundwater data and how recharge happens. The good thing about this is we have a lot of data from the government of India, especially Central Groundwater Board, with all these well locations, around 15,000 wells. Okay. And all of them are given as data as state-wise, district-wise, and block-wise. You can go into these data sets from online or the CGWB water book, the handbook they call every year, annual book they release. And it is very, very informative of giving the situation of groundwater in India. Sometimes it is published once in 2 years, but sometimes annually also. And the groundwater yearbook has all these details of how many wells are monitored, which are the locations turning critical, those kind of things. Okay. And it can be used with other data to also look at how the groundwater situation is. Is it going down? As it's showing here, the 4 points, which is coming down. So the groundwater board data is collected 4 times in a year. It is the pre-monsoon, post-monsoon, and then you have a winter and then a summer. Okay, so somewhere also in between the monsoon also the season can be taken. So all these 4 months are very, very important, and it depends on where you are. If it is south of India, it is a different calendar, but at the end it takes 4 times, and they give you the month of which they take. So let's see how we could use this data to estimate groundwater recharge. So this is a very, very widely used method. I'm taking the notes from the USGS, US Geological Survey. And you could see that the water table fluctuation is best for shallow aquifers, not deep aquifers, because it readily depicts how the solid material will let water flow. Like the specific yield is one of the important parameters. So all you have here is you have your water level on your y-axis and your time on your x-axis. The groundwater level is down, and it is called discharge or pumping. We are not worried about it. We are worried about the recharge. So suddenly there is a recharge event. Maybe water rainfall occurs and a lot of recharge is happening. So the water level rises. So this is the water level in the well. Okay, so think about a well, and this is point A. Okay, it is down, it's going down, and then suddenly after some time point B happens. Okay, so the water level is rising. So now you need to calculate what is the recharge, which is our objective. How do you do that? You take time t equal to 0 to time t equal to tj. So where it actually starts to rise and where the peak is taken. Okay, that is a 2 times or whatever time frame you're going to look at for the recharge. So you have a zero stop, and then what time are you on? It can be daily, it can be hourly, etc. So our TJ, which is the recharge occurring between two times, T0 and TJ, is nothing but the specific yield of material, of the soil, of the rock, times your change in the hydraulic head. So you have the time T0 and TJ, and the peak water level rise attributed to the change point. So from here, the peak level is TJ. Okay, at TJ, the peak level is HJ. We call it del HJ. Okay, so that difference, in the head from T0 to TJ is called as del H. See the symbol del? It's like a triangle. That means change. The change in head, hydraulic head or water level because of recharge during a short time period is called del H. And that time period, the water is raised to here. It is del H, which is nothing but this minus this one. Okay. And you just multiply by the specific yield, you get the recharge, because the specific yield is a function of the liquid and the rock material. It tells about how much water can actually flow through gravity, and the remaining water actually is available for water for plants and stuff. So here the most important factor is not only groundwater data, because you need to have a lot of data accumulated over time, and sometimes you do have meters which are monitoring these data at a longer time interval. The most important factor is the specific yield. It's very, very hard to estimate and expensive. So what the GEC has done, it has given you all the different types of formations or solids or rock material, however you want to call it, sand, or your soil type, etc. The formation and the recommended value. Then there is a range, minimum and maximum value. So in Indian terms, these are the recommended values. In the international terms and globally, this could be the range. Please understand that these are rock materials, weathered rock materials under the ground, so it doesn't have boundaries of national, climate, etc. Okay, it is just how bad the rock is weathered or how young the rock is. It determines the connections, the pore space, etc., etc. So let's look at the most important factors here. You have the formations: alluvial, sandy, silt, clay, all having 16%, 10%, 6%, pretty high. So in the alluvial, we can say it is pretty high. Then the next is your hard rock aquifers. So again, the Indian government JEC committee has just divided it into two types, A and B. A is where the alluvial and high yielding aquifers are, whereas B is more the hard rock, the central India part, where groundwater is really, really scarce. So you have all these having specific yield around the range of 3, 1%, 1.2%, etc. So it's really, really low, except the karst limestone, which is all these caves and rocks, which is not much in India. So most of the area is under hard rock. So this is the value that you should put in this equation. You can take the data, this data, from your groundwater wells from here. So I'm giving you a method based on GEC and the data where you can take and do these equations. You can go to GEC's website or Central Groundwater website, download the data for your particular area. And for that particular area, the CGWB handbook gives you what type of rock it is. Then you go back to this equation, plug the specific yield from this table. You have already the water level difference between the pre and the post monsoon. Okay, the pre is summer, and after the summer, the monsoon comes. So if you take the reading between the pre and the post monsoon, then you can know how much water level has changed. So whatever you're going to calculate is the recharge for 3 months, because pre and post is 3 months. Okay, the time between the pre-monsoon and post-monsoon is 3 months. So this is how you would use the GEC estimation method with the groundwater data and a specific yield to estimate groundwater recharge. I hope you understood the principles of this, most importantly, the estimation methods. I will see you in the next class where we'll look at a couple of more equations. And also, this is the same thing to do discharge. Please understand that recharge is a process from low groundwater level to high groundwater level. Water level goes in, or water goes in, groundwater recharge happens. The water level is pushed up, that is recharge. What is discharge? Your groundwater is at high, it is pumped out, so water is lost, it comes down. Or it can naturally come down because it is discharging. Okay, so you can use the same or similar methods because the data is the same. And that is why the Central Groundwater Board collects data 4 times a year, beautifully capturing the pre to post, which is your recharge, and the post monsoon to the next pre monsoon, which is your discharge, how much water you have taken out. With this, I conclude today's lecture. I will see you in the next lecture. Thank you.